Okay, so this afternoon we're going to switch gears a little bit, and we're going to first talk about sigma, pretty important issue, and Linda will go over that. Then we'll talk about vertical ground motions, and we'll come back to finite fault simulations and talk a little bit about the validation scheme, the preliminary validation scheme. So first talk is Linda Alatic.
Okay. Good afternoon, everybody. I'm going to talk today about the different tasks for the Sigma working group, the critical issues, and the data needs. First, I want to start by saying that our working group is common for NGA East and NGA West 2 projects. We are charged with the aleatory variability of ground motion. We're also going to work on the epistemic uncertainty of sigma, which is sigma-sigma. But we are not working on the epistemic uncertainty of the median ground motion. That's handled somewhere else. My talk today is divided into two parts. First, I'm going to go over briefly single station sigma background. I'm going to introduce the newest and hopefully improved terminology and definitions. I'm going to talk briefly about the approach to single station sigma and what that entails in terms of critical issues and data needs. And the second part, I'm going to go into detail and talk about the different tasks for our working group. So first, we all know what sigma is. It's the total standard deviation of the ground motion. The residual delta is the misfit between the observed ground motion and the ground motion, median ground motion predicted by the model. This total residual for an earthquake E at a site S is divided into two parts. The between event residual, delta BE for earthquake E, and the within event residual, delta WES for earthquake E at station S. So in this new terminology that we adopted, we try to make things more intuitive. So B stands for between, W stands for within, E is for earthquake, and S is for station. So if you look at the plot here, for example, delta B1 is the between event residual for earthquake 1, and it represents the average misfit of the ground motion for this earthquake with a median ground motion predicted by the model. Delta W1S, for example, is the misfit between the observed ground motion for earthquake 1 and at station S and the average, the earthquake-specific median prediction. And this new terminology, the between event standard deviation, is referred to as tau. The within event standard deviation is phi, and sigma stands for the total standard deviation. So how do we go from sigma to single station sigma? Well, if we have multiple recordings of the ground motion at a certain site, we can estimate the systematic site effects and remove them from the aleatory variability of the ground motion. So the key step here is to estimate delta S to S, which is the site-to-site residual, and which represents the systematic deviation of the observed amplification at this site from the median amplification predicted by the model. This table here summarizes the terminology that we're using. So under ergodic assumption, we had within event residual. Some of you know it as the intra-event residual, delta WES. If we remove the site-to-site residual from this within event residual, we obtain the single station within event residual, delta WSES. The single station within event standard deviation is phi SS. The single station standard deviation is sigma SS. Basically, we adopted this subscript SS to refer to single station. I know that this terminology is still new for most of the people here, and it takes some time to get used to it. So for that purpose, we put together a terminology document. It's posted at the peer website, and it basically describes the various notations that we're using. So the advantage of using single station sigma is that it reduces the aleatory variability of the ground motion. This table here shows a summary of the results from previous studies that computed single station sigma and compared them to sigma. And we see here that there was a reduction of anywhere between 9% and 23%. However, I want to mention that this reduction is not completely free. Basically, it means that there is an increased epistemic uncertainty if you don't have site-specific data to constrain the median of the ground motion. Here I summarize the approach for computing single-station sigma in a very simplified way. First, we need to compute the within-event and between-event residuals using the two-step method or the random effects approach. After having these residuals, then at each site with enough recordings, we need to compute the average site-to-site residual. Then having that, we can remove this site-to-site residual at each site from the within-event residual, and we get the single-station within-event standard deviation for each site as well as for the full data set. So the key here is to estimate the site-to-site residual, and to do that, we need to have enough recordings, and we need to define what constitutes a sufficient number of recordings at each site that we can use. This here is an example of the within-event standard deviation, CSS, at different sites, plotted versus the number of recordings at each site for California at peak ground acceleration. Basically, each data point here on the plot represents one station, and we can see from this plot that the average CSS becomes stable for a minimum number of recordings of really 5 or even 10. So this gives us an idea of what sort of needs we have in terms of minimum number of recordings per station. This is again a plot for the California dataset using the Abrahamson and Silva 2008 dataset plus the small to moderate magnitude data that Brian Chu collected. This here shows us the single station within event standard deviation binned by magnitude and by distance. And we can see here that for magnitude 4 to 6, CSS is dependent on the distance, and the largest CSS is observed for short distance and moderate magnitude. This also gives us an idea of what sort of trends we might observe for this project, and that really we need also to have data at short distance and moderate magnitude to be able to see such a trend if it's applicable for us. So now I will go into more detail about the different tasks of this working group. Our main objective is to develop multiple single-station sigma models for central and eastern U.S. and for western U.S. that will be used by the GMPE developers. And as it was brought up on Monday, the issue of sigma models, I want to say that we are also going to develop ergodic sigma models for central and eastern U.S., but I'm not going to talk about it more today because the scope for this task is not yet well defined. We're also going to evaluate single path sigma to see what sort of applications we can expect in the future, but we're not going to provide single path sigma models for central and eastern U.S. And finally, we're going to evaluate the effects of soil nonlinearity on single station sigma. Since data in the eastern U.S. is less abundant than in the western U.S., especially for large magnitude, we're going to evaluate single station sigma for eastern and western U.S. To see if, and we're going to compare the single station sigma at small magnitude between active regions and stable continental regions, and see if we can apply single station sigma that will be evaluated in California, for example, to the east. There has been work on single station sigma. We're going to take advantage of these studies. Basically, BC Hydro evaluated single station sigma for subduction zones. Swiss Nuclear is currently evaluating single station sigma for California, Taiwan, Japan, Turkey, Mexico, French Pyrenees, and Switzerland. We're going to use the results of these studies for evaluating single station sigma. So going into more detail, task 1 involves developing a set of guidelines for evaluating single station sigma. These would outline the methodology that we will use and also answer questions like how do we define the sufficient number of recordings per station. We have the Pegasus guidelines, and we're going to use that, and we will modify it as we need to. Task 2 consists of computing single station sigma for central and eastern U.S. We're going to evaluate different trends like magnitude and distance dependence, main shock and aftershock dependence, regional dependence, and VS30 dependence. And for this task, we need the flat file of the data for central and eastern U.S. This is here an overview of the data for central and eastern U.S. that is still preliminary and it's available for this project. We have a total of 16 earthquakes. All of them have 5 or more recordings per earthquake, which is good for us to obtain a reliable between event residual. This plot here shows the frequency of different number of recordings per station, and we see here that most of the stations recorded only one earthquake. So out of the total of 642 stations, only 9 of them have 10 or more recordings per station. Clearly this is not sufficient for us for computing single station sigma for central and eastern U.S., and we need more data. Task 3 involves evaluating single station sigma for other regions based on the Pegasus project, on the BC Hydro project. We will also evaluate single station sigma for Wenchuan earthquake. In fact, we have a visiting scholar who's working on that, Mr. Yu. For the Australian data, we're going to also use it for our single station sigma evaluation. This is an overview of what we currently have for Australia in terms of data. We have a total of 58 earthquakes. 54 of them have 5 or more recordings per earthquake. And in terms of the number of recordings per station, we have 35 stations with 5 or more recordings and 26 stations with 10 or more recordings. We will use this data for evaluating single station sigma and any additional data from Australia that meets the criteria of 5 to 10 minimum recordings per earthquake and per station would be useful for us. Task 4 involves comparing results of single station sigma for different regions to those of central and eastern U.S. We will evaluate the stability of single station sigma across different regions to see whether we will be able to see any trend there. Task 5 involves computing single station sigma for shallow crustal earthquakes in active tectonic regions for horizontal and vertical ground motion. We'll also evaluate trends such as magnitude and distance dependence, main shock and aftershock dependence, regional dependence, and VS30. For that, we need the flat file of the small to moderate magnitude data in Western U.S. and the flat file of large magnitude data for Western U.S. Task 6 involves comparing the results of single station sigma for central and eastern U.S. and Western U.S. to see if at small magnitude they are comparable and that if we can possibly use single station sigma from the west and apply it to the east. Task 7 involves developing candidate single-station sigma models for central and eastern U.S. and for western U.S. These models will depend on the different patterns that we will observe with the data. Some examples are constant single-station sigma model, magnitude-dependent model, and magnitude and distance-dependent model. We will also evaluate the possibility of simplifying the dependence of single-station sigma to a single parameter. Task 8 involves preparing the single-station sigma report that would describe the data sets, the analysis performed, and the different single-station sigma models. Task 9 involves evaluating single-path sigma for central and eastern U.S., western U.S., and other regions. And Melanie Walling at USGS is currently working on that. This task is for exploring the future application of single-path sigma, but we're not going to give single-path sigma models for this project. Task 10 consists of evaluating the effects of soil nonlinearity on single-station sigma, using existing simulations and performing additional ones if needed, and also using empirical data. Task 11 was suggested on Monday, and it involves evaluating the applicability of the lognormal distribution to the upper tail of the ground motion distribution to see also if there is any evidence for truncation of the ground motion and at which level. Additional tasks that we can think about, but they're not really defined for the project yet, are, for example, comparing single-station sigma from empirical model to those from ground motion simulations. And this can be brought up during the discussion. So in summary, what we need for the single-station working group is data, and lots of it will be good. So we need multiple recordings per earthquake, minimum of 5 to 10, and multiple recordings per station, also minimum is 5 to 10. We need the data for central and eastern U.S. We need small to moderate magnitude data for western U.S. and large magnitude data for western U.S. And that's it. Thank you.
Don't go anywhere. Does this just go backwards and we'll have things? All right. So what Linda has run through, you can see currently there aren't a lot of candidate models for single-station sigma out there. This is something that's new. There's been some studies of it, but nothing that have been comprehensive evaluations. What we're trying to do here is take advantage of what's happening in the Pegasus project and try to use results that they're having and the work that they're done, and then improve upon that in trying to develop our single-station sigma models. So I think I've started in terms of data needs. Linda went through a lot of tasks. It's a whole lot of stuff, so let's go back through them again a little bit, not in the details, but in the big pictures so that you know what we're trying to do again. Guidelines, this is a topic, for those of you who haven't been in the exciting world of Sigma, is a topic that a lot of people around the world are working on all at once. And so the Pegasus project really has been the first place that tries to integrate all this stuff, and Fabrice Cloton has been doing this with Adrian Rodriguez-Merrick, pulling all these things together. So we're going to have the luxury of having them do quite a bit of the initial work for us, and then we can use those as initial candidate models to start with. This guidelines part is done. It was just so that we would all be calculating the same thing for the different data sets that are being used. Your task 2, which is fairly straightforward, we haven't done any of this for the eastern U.S., so this is a brand new thing. I think we heard Bob Herman say that he could get a fairly large set of recordings with at least 10. Is Bob still here? looking. I don't see him today. Okay, so once that data set comes in, I think that will substantially expand things. I believe the real key is not as much of the details here as this problem. Okay, so the data set that we have now from Chris simply will not do. All right, will not be able to, or cannot meet our needs for addressing the problem. We need a lot more than 9 stations with 10 recordings. So we've got to get that up to, it would be nice to have something like 50 stations or something like that to be able to start to get numbers that we can rely on. That's probably the first thing that we have to have in moving this forward. So we'll be checking the single station sigmas from the Eastern U.S. data set with things calculated in a consistent way from all of these other regions, Taiwan, Japan, the European data sets, and the California data sets. One issue that we would have is if there's anyone out, if you know of any other sets of data where we have lots of repeated recordings, or stations with lots of recordings, that would be an additional set to look at. Linda didn't talk to you too much about the details of what's happening in Pegasus. I can give you a bit of a sort of the one-line summary is, while we see large variations in total standard deviation, the classical sigma around the world, the single station sigmas are much more stable. So we see much more similarity in the values between Japan and Taiwan and California and Europe than we do when we compare just the standard deviations that are published in attenuation models. So that's an encouraging feature that we may be able to transport some of that information to the east, but that's what has to be verified in this first or second test that Linda has talked about. Are there any other data sets that any of you are aware of? Ralph? Come up, please.
I'm going to presume that since you're working with Fabrice Coton, that you've been looking a lot at the KNet and in particular the KICnet data. And it raises the question because in the KICnet data you have both the downhole and the surface, and it'd be very interesting to know whether or not they show the same variability in sigma, uphole and downhole, given that one of them is supposedly in rock.
I know that Adrian Rodriguez-Marek and Fabrice Coton, they just submitted a paper exactly, dealing with downhole and surface single station sigma. So we will, look at the results and see.
I also was funded for the same thing, so I'm going to come up with an independent assessment of that for KICnet. So.
Since nobody wants to tell you the answer is the single station sigmas at the surface and at the borehole are very similar. So that takes out a lot of what we've seen of the differences between it. So this just appears to be a more robust parameter to be working with. Okay? So when we see a single, we'll see it say, in fact, at the break, I may be able to pull out some pictures to show you, but the standard deviation may be 0.8 at the surface, and it might have been 0.7 or something, quite a bit lower at the borehole, but then they're both around 0.65 or something when we do the single station sigma. So that reduces quite a bit of the difference that we've had. Are there other data sets that you're aware of?
The one data set that comes to mind, since we're especially looking in the east at this magnitude range of 4 to 5, is the aftershock sequence of El Mayor, because the aftershock sequence, Bob's shaking his head, but the aftershock sequence of El Mayor has got a number of magnitude 4s that are north of the border, and there must be 20 or so in this range, and in fact it generated several magnitude 5s well north of the border as well. And they're recorded at the borehole array, the Borrego Valley downhole array, which has rock site and surface. And now I'm not sure, I think the rock site at borehole is not working, so there's really only the surface site.
I know in NGA West we had issues with aftershocks and dealing with them separately, so I can't remember now whether we dealt with sigma being differently for aftershocks. I know we dealt with the medians.
Walt and I, in our model, dealt with aftershock sigmas, or checked that, and actually ran the regression once with allowing separate sigmas to come through for aftershocks and main shocks, and there was no significant difference between the two. So we found a median shift, but the same within event term.
I should know, but I can't remember what we did, Brian.
Brian, do you want to come say what you guys did? And we have to get you to, this is Brian Cho coming up.
For our NGA model, we model the difference in the mean amplitudes between the main shock and aftershocks, and also model in the sigma the difference between main shock and aftershock. So, yeah, there is some difference in it, but not. I don't remember. I have to go back and check.
So that will be something to just make sure that we are, if we're going to use aftershocks, that we're getting the similar standard deviations. Yusuf?
I think maybe Linda mentioned also Wenchuan earthquake in China. I think they have 64 aftershocks, and we have a visitor from China who is doing analysis of single station sigma, so we can check what's going on also with that.
Did you have that in your data sets to look at the Wenchuan aftershocks?
Yes, and we started working on this,
Mentioned that, and we don't have the results passed back to it. Part of the work for the sigma, we don't just need the ground motions, we need residuals, which means someone has to derive a model for each of the data sets to back out the residuals from. Okay, other data sets that we are actually going down pretty small in magnitude, down to at least to magnitude 3, because to get enough recordings at a site, you have to sort of bring in some smaller magnitude earthquakes, which is why we've gone on to this whole issue of now we need ground motion models that work well down to small magnitudes so we can get the residuals properly. But those residuals from these small earthquakes appear to still be decent predictors of the site term, which is back to most of it is in the linear range. Let's look at your next. So you've got, these are the data sets. Again, are there any other data sets that any of you know of which would meet this data need that we have of, again, a goal of 5 to 10 recordings per station and 5 to 10 recordings per earthquake? Okay. The Australian data set looks to be a valuable one. We haven't started on any of this yet, but it's got a lot of recordings here, 26 with 10 or more stations, so that's going to be, I think, a useful one for us to include in the sets that we're doing. This is based on what's available now, right? And then, Trevor, do you have an idea of how that would change with your other data sets? Sorry, bringing you back to your resource expert for us on data sets.
Yes, as Norm said, I'm now a resource expert. So the data set that Linda already has is essentially probably 2/3 of the Eastern Australian data set. So I don't expect that those numbers are going to change too much. However, there is the data set from Western Australia
and I guess it's still to be determined whether that data will be applicable for NGA East, but most of that data was recorded from an earthquake swarm, so there were essentially 60 earthquakes where most stations would have recorded those earthquakes.
That's potentially a very good data set for looking at this kind of information. Okay. So this is task quickly is comparing the regional differences. As I said before, so far we've seen very small regional differences between single station sigma as compared to the standard sigma. The key I think we're going to have to talk about is how we start to get into finer details about the sigma dependence. Magnitude dependence, distance dependence, aftershock, and so forth dependence, and whether, did you just do that to me? You started to type, and the thing went, yes, that's all right. No, thank you. Sorry about that. Did it just, clicked on the slide? I remember that part. Okay. This is going to be our key issue is the comparison. So we'll still be short on large magnitude data in the eastern United States. And all that our plan has been to compare similar magnitudes and similar distances in California or other regions versus that which we have in the central eastern U.S. And then after that, assumptions of scaling, right? And there's really nothing else that we're going to be able to do about that. If you want to talk about your candidate models and the uncertainty, did you talk much about sigma yet?
No.
Why don't you cover that, and then we'll get into the simulation.
We're going to provide different single-station sigma models. Like I said, it depends on what trends we will see with the data, but possibly constant sigma model, magnitude dependent, magnitude and distance dependent. We won't provide weights, right? Yeah. So
one issue for us to think about is our current structure, our thought process is we have sets of median models, which we've been talking about for today or the last few days, and then we have a standard deviation model. And whether those things are correlated, does one standard deviation go with a particular model, or are we going to keep those as independent? The approaches that we're using here essentially are heading down the independence path. That whatever sigma model we have is applicable to any of the standard or of the median models. And whether or not we ought to be trying to track those things and say a standard deviation model goes with a particular median model. Dave, do you have a concern with that either way? Or he's shaking his head no. I think he's... Yes?
This approach that Norm just mentioned, I think it seems promising because they tried different complicated and simple models. They tried different simple as well as very complicated models, and more or less they computed the same. Obviously, the median values are different, but the same standard deviation. But they are digging into that. If they prove it, it's going to help and simplify the whole life.
And then I think the big remaining question that we're going to get to is... where did you have what do we do with combining the information on sigma from the simulations and the empirical data sets? So what Linda has described to you so far has been all the empirical type of an approach. From the simulations, if we get out all the things we were talking about this morning, proper distributions, PDFs of input parameters, then you come back out of that simulated standard deviation. And we haven't talked or really worked through that process yet. We've done this before where we again track modeling and parametric uncertainties in the simulations and put them back together. And whether that becomes a branch on our approach to the standard deviation or not. Yeah, Ken.
Ken Campbell, you know, when Brian mentioned that they did get a difference in sigma between aftershocks and main shocks, I was thinking that one thing you, I guess, need to be aware of here in these sets is the potential correlation between single path and single station sigma. Now, maybe in your methodology you remove that, but some of the aftershock sequences may be clustered such that you're also sampling a more refined part of the crust. So you may get a little reduction there, additional reduction there. So I don't know. I haven't seen these things, and maybe you've already looked at them, but that would be an issue, I guess, in using all of these data sets that, you know, to make sure that you try to make sure you're not double or taking paths and putting it in their stations.
Yeah, so I think the comment is if we have in particular aftershocks and large numbers from a single region or small source area to our site, we will be effectively getting the single path sigma, which is significantly lower than the single station sigmas. Numbers that we've seen have typically been closer to numbers as low as 0.4 for single path sigmas, which are very small numbers. That's a topic, did you write that down? Because we're going to have to, I think, watch for that with the aftershock sequences. I can think of a few approaches to deal with that, but let's, I think in our task list, we need to be sure that we're careful about evaluating that part of the problem. Bob, do you have some ideas? Come on, okay.
So I have, this is Bob Young, so I looked up what we actually did after staring at Brian. So we have 0.06 log, natural log units higher in the high frequency range for aftershock sigma. And it goes away at long periods, probably because the aftershocks go away from long periods of the data. Well, partly aftershocks go away, so I don't know whether it's there or not.
So that's going the opposite direction of what we just talked about. But
that the aftershock signal is higher.
Okay, aftershock signal. Okay.
Well, we don't have a lot of. We don't have our data set that.
He just wants you to say it again.
Okay. In Cho and Young's, the aftershock standard deviation is 0.06 units higher than the main shock. There's an additive term that we put in for aftershock sigma. That's the aftershock sigmas are a little bit higher than main shock sigmas. But we don't have huge data sets like you're looking at here where we're sampling a lot of aftershocks from a single earthquake. There are typically a few aftershocks that show up in NGA, not lots of them. So I don't know if that the issue you were talking about for single path would have affected those data sets.
Thank you. Any other pitfalls people can think of that we may have to deal with? I think what Ken mentioned is an important one. Brian, do you have anything on single station sigma issues that you think need to be addressed? No. Okay. Yeah, what are we going to do with simulation? So this comes back to we can leave it as a task to address those. Those will come out. I think it's important that we addressing them from numerical simulations is a big deal. Okay, so it's not let's just do it and see what happens because of the large cost that's involved in getting all of those parameters properly brought along. Yet it does provide us a nice way to sample what may be truly future earthquakes instead of the standard deviation from those earthquakes that we happen to have ground motions from. That's your main comment. Dave or Paul, or let's bring Paul up because I think he's got something to say. Paul behind you first. And then you're next, Dave. Thank goodness.
Well, I'm not really a 3D finite difference or finite element modeler, so this is half a statement and a half a question to one of them to comment on this too. Of course, for looking at this single station sigma, one might be able to set this problem up for simple plane wave input. You want to integrate the response over all possible azimuths of incidence. So it might be able to set the problem up on a smaller domain than the entire source path, the entire distance from the source to the path. The problem, though, is going to be that you can't look at this problem in a simple layered medium because the scattering that you get from heterogeneity in the crust is probably going to be the dominant factor, and whether there are good models of 3D heterogeneity in rock that would enable you to do a sensible numerical calculation, I don't know.
So on this topic, we have to keep ourselves doing something within the scope of what we can deal with, and that is going to be essentially 1D velocity structures. So the scattering that Paul is talking about in terms of 3D effects will not be included in the simulation, but we'll capture it implicitly, or we hope to capture it through our modeling aleatory term from the model validation. So remember, we're going to keep using a fairly simple crustal structure and so forth to go forward with the idea of all of the shortcomings of that assumption will show up when we have a misfit in the validation between the predictions and the observation. And that piece of the standard deviation gets brought along and added to the standard deviation we get when we vary parametrically source parameters such as slip distribution and rupture velocity or whatever parameters that we have free in the model. So we'll try to get it, but that is back to an empirical number, right? So that's really then not a simulation driven. The simulation driven part is really only going to be in the things we were talking about this morning, where we generate multiple source inputs and then propagate those through and see what additional variability those provide, as well as the variability as mutually that we're going to lock or average out to a model that's just based on distance and not based on azimuth. Does that make sense? Dave said no. Okay, so when we run our simulations, we'll run them as a racetrack, let's say around the fault at 10 kilometers. So your finite fault simulation may well produce different values in all those locations at 10 kilometers away. We'll take a median, and then that variability gets thrown into as well our parametric term. That's not part of so that part and the source part are added to the empirical piece, which is just based on comparisons of simulations to past observation. Okay.
Gabriel Toro, and I have a question. It may have been answered before, and if so, I apologize. And I may be wrong. I don't quite get Linda's terminology, so I may be making a mistake here. But is this project supposed to cover anything on how you estimate the site bias on a site that is not well known, or a site that is moderately well known, a site that is well known? I should know this, but I don't.
You should answer this. No. The answer is no.
No, but we do, as along the way we are, for example, having the geotechnical group do a model of how you do site response or site factors that could be more broadly applicable. We are looking at a separate part of the project that deals with implementation guidelines for single station sigma, because people will not know how to use it. Okay, so if you know nothing, what do you do? Okay, if you... We'll have the standard one, but we'll have something, and as you begin to know something, what do you do, all the way to what does a nuclear power plant do in a site characterization. So we are looking to have something separate done, bringing that project along. Go ahead.
I might have spaced out a little bit because I'm trying to take notes, but what Paul has brought up is an important issue because we're going to underestimate the variability that we would have in reality, right? If you have different azimuths and different heterogeneities. Do you want to constrain that? I didn't hear the answer, actually. So did you want to constrain that with the empirical, that part of the sigma?
I didn't bring the right pictures to talk about this. We have two parts that we deal with in the simulation sigmas. We tried it through the validations. We optimize all of the source parameters that we allow to be event specific. Okay. Then when you then compare your predictions to observations with those optimized parameters, we still have a misfit. In an empirical model, we have none of these other parameters, and so our misfit ought to be in principle worse than what we have for the simulation. But that standard deviation is intended to capture all of the shortcomings of the model due to the simplicity of the way that it's laid out. So not having the proper 3D velocity structure gets mapped into that. Now the whole assumption there is that the data that we're using to validate is representative of those same effects where we want to do the forward simulation. And in that sense, we're no better than what the empirical models do. You cannot be better than the empirical? Well, you could be a little different. What a good question is, do the empirical models systematically underestimate the source variability term because there's only, a handful of big earthquakes that we're looking at? Whereas the numerical simulations can, in principle, sample a broader range. Or did the 10 that we have actually have a Saguenay in it, right? Where if I try to take my eastern U.S. ones and said Saguenay is one of 5 or 6 big earthquakes, and yet it shows up as a huge value, I would overestimate it. So you don't know which direction you would be. The idea being the simulations may be more representative of what the true variability is as opposed to the variability we got from a small sample that we choose. And we will face this big problem in the East. What do we do with Saguenay? Okay, that's going to be, is it one out of, the few earthquakes we're looking at, or do we declare it anomalous and say it is a 2 sigma event by definition, right? This is going to be a struggle. I don't know if you have any comments on Saguenay, what to do with Saguenay, Bob? You're shaking your head. This is our one big earthquake being declared anomalous is a tough place to be, right? Martin, do you know any ideas on dealing with Saguenay in terms of variability? Okay, so Martin is saying he doesn't necessarily think it's anomalous, right? So that's another whole issue of what we need to deal with. So the simulations may be able to help us look at that, but it will be based then on what we're assuming is going into the simulations for the median stress drop. So we're into a problem of anything we're trying to calibrate on data, we're at the mercy of those events that we have and what they're doing. Yes.
So then what I see from what you're saying is that you think we will capture more variability in the simulation schemes we're going to do in a forward sense. Although, if I look at it issue by issue, in some cases we might not capture all the sources of uncertainty, but because we sample such a wide range, because we don't capture the 3D velocity, right? The uncertainty to that.
We capture 3D velocity structure uncertainty through the
range of parameters. Okay.
Not through the range of parameters, through the misfit of data and simulations where the data are collected in areas where there's actually a 3D velocity structure. So I go to California, and I go to the LA Basin, and I say I'm going to put out recordings, but I'm going to use a 1D velocity structure. I'm going to have a misfit.
Okay.
That misfit we declare to be part of or due to all of these unmodeled features.
Okay, thank you.
Okay, but Saguenay is going to be a different issue. I would not say using numerical simulations will necessarily give us a bigger variability than the empirical data. It depends if the empirical data were themselves too narrow or too broad, or were they typical, right? And that's how do you get statistics off of small numbers of samples? It means Christina's saying import data from other regions, because I have to repeat everything you say. That's one way to get at it, okay? And Bob is shaking his head no. Not a lot of other places to import. So we're data poor, okay? We're going to have to be using, and part of this are small magnitude data to try to figure out what is the variability where we have data. We can compare that to California variability, and then our whole question is, can we then, if those are comparable, can we scale or assume the California ones are transportable? If they're not comparable, can we make the correction in the same way? We're going to have a whole lot of issues to deal with on standard deviation. And this is a parameter that matters in the end to the whole hazard calculation. Dave, you've been quiet on this issue. You're throwing up your hands as to what to do. So I think we don't need to deal with the Saguenay issue yet. That will be one of our topics as to how to handle that. But we need to go through all that we can in terms of compiling our information. It will primarily be small magnitude information that we've got to work with in the East, and then simulation information as well. Anything else that you can see in terms of data needs for this topic? Yeah, John.
Yeah, there was one part that you mentioned, Norm, about the fact that the sigmas are calculated from residuals. And so we have the data of what we have, but we don't have a model for the central eastern U.S. So you didn't quite make that clear of what is the model the data will be compared to, because this is all being done, of course, before the final product's available.
That's a good question. We will use a very basic ground motion model that have only magnitude and distance in it. And Sanaz, I think she tried basically, more complex models with very simple models, and there wasn't a lot of variation in the sigma. So we can use a very simple model and use it for all the data. Yeah, with the side term, yeah. Simple.
So simple. So a model will be derived based on the Eastern U.S. data. We have to derive a new model that is not our ground motion model for predictions, because we don't care how it extrapolates, but a model that can capture or basically take out the magnitude, distance, and site scaling, so we can then work with the standard deviation.
That's based on the empirical data?
Correct. So we simply need something that's part of what the guidelines that were set up on the Pegasus project. This is how you have to do the regression. So we need either a two-step or a random effects regression, so we have the two terms, and then how do we get the site terms out and so forth. So we do have to create a model. What Linda was saying is we can use a fairly simple model because sigma doesn't change very much based on model complexity. You can add all sorts of things and parameters, but if it's 0.6, it may go down to 0.59, but it's really hard to move sigma. You said.
In fact, this question, it was my fault. I didn't elaborate on that. In fact, Sanaz and Linda are going to write a paper or a report and so on to establish this fact. They are going to use very complicated model, very simple model. Obviously, the median values are different, but they are going to show it that hopefully the standard deviation is not that sensitive. And then that is the basis of what Norm says. If they can establish that, so it means that a standard deviation model can be applicable to various different GMPs.
Other comments on how to handle single station sigma. For the total sigma, our traditional sigma, there's two approaches. One is to just add in the site term back into it, and the other is to just try it directly from the data sets as they are. Linda was asking, are we only computing sigma for the Central and Eastern U.S. data set? The charge, our deliverable, is a single station sigma and a total sigma for the Eastern U.S. Yeah.
So, as Linda mentioned, this is a joint working group between West and East. So obviously for this workshop, the focus is Central Eastern North America, but that working group is working parallel with the database for the West to basically to do the same thing with shallow crustal earthquakes. Exactly. She said also for NGFS, I said yes.
Okay. Any other comments? Ken, do you have any other suggestions on sigma? Those of you who have worked on this for years on years. No. Okay. We'll probably get quite a bit more of this as as we see results from Pegasus. I think will be the first ones that will then come back with a set of models that we can begin to look within and see how the Eastern U.S. deviates from those models. So let's stop here. We're like an hour ahead, and I would just jump to Sanaz, verticals. So.
Okay, so I'm Sanaz Rezaian, and I just wanted to go over the big project plan for vertical working group and the critical issues and data needs. Good? All right. Okay, so for the working group, currently we have 4 members, Gail Atkinson, Yusuf Luzarnia, and Walt Silva, and myself. And the big goal, obviously, is to develop a model for the vertical component of ground motion in Central Eastern North America. This is going to be done through application of V/H spectral ratios. And development of this model for East is going to be preceded by development of GMPE in West. This is part of the NGA West 2 project, and looking at V/H ratios in West, and then making appropriate adjustments for Central East North America. The current plan is to have one set of models to be developed by this working group. If we have more than one model, we also come up with the epistemic uncertainties. So in terms of the available literature for modeling vertical motion in East, we have two studies. One is the study by Siddiqui and Atkinson in 2002, and the other one is the part of the NRC report in 2001. Both of these studies calculated V/H ratios empirically and tabulated the recommended ratios. You can see the main tables from the first study and the second study here. And both of these two studies are focused on rock site conditions. Here you see the database that was used in each one of these studies. The first paper used data from Geological Survey of Canada. They had quite a bit of earthquakes with small magnitudes and some earthquakes with magnitudes between 4 and 6. They used hard rock site conditions with shear wave velocity of greater than 1,500 meters per second. The second study also had a lot of earthquakes with small magnitudes, less than 5, but they also had 3 records with from 3 events with larger magnitudes. They also used records with hard rock site conditions. Here you see an example from the NRC report. Basically what you see here is the V/H response to spectral ratios versus frequency. These two horizontal lines, they indicate the 2/3 ratio and 1. So you can see that at some conditions, the vertical motion actually can be much greater than horizontal motion. So this just signifies the effort that we are doing for modeling the vertical ground motion. So we are going to develop models for the median and aleatory variability of V/H. Hopefully we can do something better than just tables. And we are going to do this for both rock and soil site conditions. We are also going to look at the dependence of this ratio on factors such as the spectral period, magnitude, distance, the factors that have been known to be important for V/H ratio in West. This is basically our big project plan, which is divided into 2 main stages. In the first stage that started in June of 2010 and continues until October of next year, we are going to develop V/H spectral ratios for Western United States. As I mentioned before, this is part of the NGA West 2 project. So we are going to use our results from this study and sort of build upon it and develop proposed guidelines for V/H in Central Eastern North America. The first step in our working group was to develop preliminary models for the vertical motion. This is where we are currently in the project. What we have done so far is to compile a database of vertical ground motions. It's almost completed, and we have also developed preliminary models for the vertical component of ground motion for both median and variability. When we did this, the assumption was that we have a linear soil and no basin effect. So very simple models just to look at the patterns of the vertical component with earthquake and site characteristics. There is another group that's working on modeling the vertical site amplification factors. They are going to look at nonlinear soil effects as well as basin effects, and hopefully their work will be completed by March of 2011. So once we have this model, we are going to look at the vertical to horizontal response spectral ratios. This ratio is obviously used as a factor to estimate the vertical ground motion from the predicted horizontal component, and many studies have been done recently in Western U.S. They show that this ratio depends on factors such as spectral period, source to site distance, local site conditions, and some other parameters. In this slide, you see a figure that I took from the study by Buzornia and Campbell in 2004. This is one of the best studies that's available in WEST, and it has been implemented in NEHRB 2009 design provisions as well. You see the effect of magnitude, distance, site conditions, and faulting mechanisms on this ratio. Again, these horizontal lines here, they indicate 0.5, 2/3, and 1. There was another study also done very recently by Abrahamson and his students. They concluded that most of the results were consistent with those of Buzornia and Campbell on rock site conditions, but they did observe higher ratios for shorter distances on soil, which is mainly due to larger soil nonlinearity in the horizontal direction. You can see the effects of magnitude, distance, and site condition having almost the same trend. There is another very recent study also, which was done in Europe, for Europe and Middle East by Acker and Bummer. They also overall observed that the V over H trends are consistent with the other two studies. In this figure that I took from their study, you can see the three methods being compared for rock site conditions. So in our working group, after modeling the vertical ground motion for Western United States, we are going to closely examine V over H spectral ratios and also look at their dependence on earthquake and site characteristics. Back to the big project plan. After we do this, the GMPs for the vertical motion, they have to be finalized and be checked by the NGA developers. So after these are finalized, we re-examine V over H ratios, and the entire effort should be done by October of 2011. The final report and documentation is due in March of 2012. But meanwhile, we are going to start on modeling V over H in Central Eastern North America. The first step is to look at the database that we have in the Central East North America and calculate the V over H ratios. I'm not going too much into the database detail because we have been talking about it for the past few days, but basically we have a version of this database that has been released, the database by Chris Kramer, and we are waiting for the small magnitude database. The site amplification factors are going to be modeled analytically. So due to lack of data for intense ground motion recordings, the effects of soil nonlinearity is going to be modeled analytically, and then we are going to validate them by comparisons with the few data recordings that we have. In modeling, one important issue is the contribution of P-waves and S-waves to the vertical component of ground motion, which needs to be examined. And one relative study that we have right now on modeling analytical motions was by Bresenes et al. In 2002. They did their study for Western United States, but we still can use their results and re-examine them. So what they did was to examine the validity of the assumptions that are made in modeling soil nonlinearities, and their conclusion was that for most practical applications, vertical motions can be modeled as non-vertically propagating SV waves, and at high frequencies of greater than above 10 Hertz, they can be modeled as near vertically propagating P waves. So what we have to do is to examine the contribution of P waves, especially at high frequencies, and sort of evaluate this theory for Central Eastern North America. We might actually examine some simulated ground motions and look at them, consider them as part of the database. One important step in this project is to compare the model that we had for V over H ratio in Western U.S. to the observed values of V over H ratio in East. And make the appropriate adjustments if it's required. So the final product of this working group is going to be a model for the median V over H, one or multiple models, aleatory variability, if we have more than one model, epistemic uncertainty. We are also going to provide the correlations between the residuals of vertical and horizontal components, which is important in hazard analysis. And all of this is going to be done for various range of site conditions and not just rock, which is the current state of practice, just for rock. So finally, the critical issues and data needs for this working group. In terms of the data, we need empirical data for East, which is currently being compiled. We need empirical data for West, which is almost done. We need simulated data for analytical modeling. This includes inclined PSV modeling, which requires definition of the inclination angle, and also vertical or near vertical P-waves. We need to do more study on this. One critical issue is the assessment of nonlinearities in vertical motion, which we're going to address by looking at recorded ground motions and look at evidence for nonlinearity in the verticals. And there is a group that's working on this currently for the NGA-2 project, and hopefully we can use the results from that study for Central Eastern North America. So let me go back here if there is any comments.
If you go back one, so I think the correlation that we're going to be after is correlation of the ratio versus the H residual, because we're going to be doing V over H's. So we don't want to, we want to be sure we're getting the correlations that we can end up using. Yeah, okay.
Okay. Just want to remind you again, the goal in NG East, as per the SSHAC process, is for us to develop ground motions on rock for magnitude 4 to 8 up to a distance of 1,000 kilometers, and that all the center body and range will be encompassed in there with the aleatory variability and the epistemic at the end of the logic tree. This project fits in as somewhat of an add-on that makes the product usable, but we're not going to go through the same detail of looking at alternative models. You mentioned here that if you end up with enough difference in modeling this, you might have different models and include epistemic uncertainty, but that's not treated at the same level where we're going to do that with all the GMPs. The same thing with site, so I just wanted to clarify that.
I think that's one thing for us to discuss with the people out there, the hazard analysis like Gabe or Bob. When we're doing verticals right now, is it enough to have our full logic tree with all the horizontal in all its glory, and then have a simpler V over H logic tree which gets applied to that whole range? Or are we going to fundamentally be missing something? So, Gabe?
I think this gets back to the issue of, are you looking, in other words, are you planning to look for a PSHA for vertical motions, or are you looking for the vertical motions that correspond to the design horizontal motions? And I think usually we're in the latter situation, in which case you can take some shortcuts and you can do something simpler.
So the question is for you. So I guess I'll return the question in another way. Do you think that if we apply the vertical ratio afterwards, do you think it's going to be consistent that if we were to do just a pure PSHA on vertical, would we get similar results? Is, I guess, the question.
Well, I think the answer is you don't get similar results, and that's what you, in fact, you don't want to get similar results. Because again, you're looking for typically, you're looking for the vertical motion that goes along with the design horizontals. Because the horizontals are much more important for design. There might be situations, rare situations where that's not the case. But typically, you are after the vertical motions that are consistent with the horizontal motions that control your hazard and your design. So to that extent, I hope I'm answering. To that extent, you can do something, or in fact, you should do something simpler for the vertical, simpler and consistent with what the horizontals, with the treatment of the horizontals. Not an independent, a separate logic tree, a separate GMPs, etc. I hope I answered it this time.
Yes, you said.
Yeah. Gabe, I agree with what you said. My question is that, is it next generation? That process that you just explained and it's being done, is it next generation or can we do something better?
I'm not entirely sure. It's not entirely a matter of quality. It's a matter of consistent. In other words, are you going to go in 2 steps or 1? And to get something consistent with horizontals, you should go this way in 2 steps. Do your horizontal, and for those same events that control your horizontals, do the V over H. In many ways, it's a simpler problem. But I think that's exactly what you need for most applications.
Are there any of our sponsors that have a different view of what they need out of the verticals? Bob, would you agree with what Gabe has just said? He's nodding his head yes. Okay, that's right. Larry, okay, great. So that will be what in our new and improved project plan, we will make that clear what our charge is on the verticals. Other comments on the approach that Synopsis described for the verticals? Anything else that we need to be thinking about? A key difference from what's been done in the past is there's a couple of things. One is actually an attempt to get nonlinearity on the vertical side. We haven't done that before, and if you ask me if this is next generation, I think that is the features that we have not done. Using analytical modeling to try to constrain that. Typically, we just use the ratios as they are, effectively assuming that they're linear in their approach.
I agree with you, but Christine made a good comment that V over H is for hard drive. Whatever, 2,800 meters, whatever is the definition of for the SHAC version of this. Is that okay?
The site version is just like the other site response part that is being brought along for broader application. Ken?
Ken Campbell. Having actually looked at a lot of these VH ratios, and one of the things that when Yusuf and I worked on our 2004 paper, one of the things that I looked at was attempting to develop a model for VH ratio rather than models for just the vertical and the horizontal components. As it turns out, and I'll go into that a little more, but that turns out to be quite difficult. But what I did want to convince myself was if we, just in a deterministic sense anyway, because sigma gets in the way, but in a deterministic sense, if you're just looking at medians, it turns out that you can predict VH ratios just as well with independent attenuation models for the vertical and the horizontal components. So that's something we definitely looked at. So we looked at that, we looked at the VH ratios, and the ratios predicted by those two attenuation equations, and I mean, there were no bias in the residual. So that was a good point, because, as it turns out, actually trying to fit a model to the VH ratio, and not a simple one, okay? So if the task is a simple model, maybe just for design ground motion, then something that Yusuf and I just worked on for the new NEHRP 2009 conditions gives you kind of a simple way of coming up with a VH ratio for a design ground motion. But if you actually want to come up with something more realistic than that, then it becomes very complicated because of the different ways that vertical and horizontal scale with magnitude, distance, site conditions, all of those things come into play. And it turns out that if you really want to do a good job, it becomes, well, we basically threw our hands up and said, let's just go the route of having the independent attenuation equation. So there's really two purposes here, and I don't know if that first purpose is there's a need for having a VH ratio that mimics ground motions more than doing a design ground motion type.
They may not know it, but your charge is a ratio that mimics ground motion. And I think what we've seen, the two studies that Sanaz referred to back here, if we go back to the two recent studies when I was involved in, and the other was Akar and Balmer. These are so Ken, I think both of these models were derived on ratio. They were not separate vertical and horizontal models that were then ratioed to get the plots. So these give us, I think, not just design, simple design spectral shapes, but give us really the variation in magnitude and distance and site condition that we're expecting for a V over H ratio. So I guess I'm not, and this was Akar and Baumler's, are very similar looking shapes that were derived. I think the main difference is they had linearity in their horizontal site response, and we had nonlinear horizontal site response, which is what drove these peaks to get really big when you get in close, because the horizontal is here damping out the high frequencies on the horizontal, but, the nonlinear damps out high frequencies, but the verticals stay high, so the ratio gets big, right? When these ratios are going up, it's the horizontal going down, not the vertical suddenly becoming really large here in application. But I think the charge to them ought to be to develop a ratio that mimics the behavior that we actually see in magnitude and distance and style of faulting and so forth. I'm not sure what the pitfalls were that you talked about, but I think we'll get to those when they try to do their models.
It's a function of the complexity. So if you have a model that's got magnitude saturation effects in it, hanging wall effects, and all of these other things, then it becomes a lot more complicated to do. The Akar-Balmer model, for example, is a much more simpler model. So when you do that, then you're dealing with a lot fewer parameters, and it's pretty much easy to carry that over to the VH ratio. So it was some of these other, like the NGA models that try doing this with the NGA models, and I think you're going to find it's a little more difficult. It's doable, but it was just that it was going to be so complicated that I convinced myself it didn't need to be done. But to follow up, in a PSHA model, of course, now you've got the difference in the sigmas, and you kind of destroy that relationship between the median values. And I think that's where you can't just necessarily take the two models and run them in a PSHA and take that ratio and expect that to be very meaningful. So.
Hey, anything else on vertical approaches that we need to consider? One issue that is going to be part of this in your analytical models, this issue of verticals have always been more difficult because sometimes they're from the P waves and sometimes they're from the SB or SB converted to P waves. This conclusion from the Brezhnev et al. Study that below 10 hertz is mainly can be explained by inclined SB waves, and when they actually looked at the part of the seismogram that was controlling the peak in the response spectrum, it was from the converted S wave. But our charge is really going to be verticals at higher frequencies than that. That's of key interest in the nuclear application. So that pushes us above the 10 hertz range, such that we need to think about the influence of just the P wave part by itself. This has not been a vertical site response has not been a topic that's well handled in geotechnical engineering. Any of you who've done projects know how poorly it's generally handled. So that I think the whole site response part of that could be also a more complicated piece than what we've done before, because how are we going to mix then? I think, did you say you're going to do them both ways, Sanaz? I'm trying to find, you had like nearly vertical here, right? This page here. So simulated values with these two things, all right, an inclined PSV model, and then also a part that's near vertical propagating P waves. How do you combine those? All right, because we're going to have different pieces of what those are, and what is the ratio? You know, do you take the larger of the two? Do you take the weighted average of the two? I don't think we've thought, this is going to have to be something that comes out of after we see the modeling, how we try to deal with this at high frequencies. Is it a jump as we're above 10 hertz to suddenly use the P wave part of this ratio? I don't have a good idea on how that's done. Do you know how that's been done in most projects that I've seen? They simply take inclined or vertically inclined P waves. When Walt does it, it's all doing inclined PSV systems, and I don't know anyone who's been trying to do both of these together. Do you know of anything, Bob? Right. So most of the geotechnical engineers will take the bottom one there, just say, I'm going to take the vertical as a vertically propagating P waves. Walt is the other side of things where it's all put in as an inclined PSV system. All right. Anything on verticals from Martin or Dave or Paul? That's you. No. Come on up, Dave.
Just a data needs aspect, because you want to look for evidence of nonlinear stuff on verticals. And this recent Darfield, New Zealand earthquake has some really nice data, and I don't know if I hope it's being included in the NGA West database, but that would be a very good data set to look for the effective nonlinearity on the V over H ratio. See? It is. Fantastic. Okay.
Anything else on V over H? No other general comments? Okay. We're ahead of schedule by quite a bit. Do you want to go to Ralph or take a break? And take a break. Why? Yusuf says why. Okay. Now we have just Ralph in the. Are there two in the app? I'm sorry. Why don't you take control here?
Okay, I'm going to go from memory because I left my agenda somewhere. One thing we have added last week after this was printed out is Ralph Alcioletta is going to go over the kind of a summary of the plan so far for finite fault validation. And I think that this will stir up some discussions that we didn't quite finish this morning that are important. So I suggest we take a break now and we come back refreshed in that mindset and be ready for discussion. Thank you. 15 minutes, so a quarter, 10 minutes to. Yeah, 10 to 3. Yeah.
No, because that's not what, it's not, I don't think so. So here she's going to do all this for soil too. What we would do, what we're worried about.
Okay, everyone. Last chunk of time. I don't even feel like it anymore. Okay, guys, we're going to start again. Last little stretch. Let's just sit down for a little bit more than an hour. We'll get through this and feel good that we achieved our goals. Can you put the slide? Oh, it's yours? Oh, okay. So we're at the last talk of the week, and then we'll have discussions and some closing comments. Ralph Archuleta is going to talk about the finite fault simulation plan, which is still in a draft status, right? Okay. It's an airy draft, lots of draft in it. Okay, Ralph.
Okay, thank you, Christine. Well, I've got to tell you, the previous two speakers really put me to shame. I mean, they had bullets and sub-bullets and all the rest, and you'll be really surprised. So the working group on finite fault simulations is really just getting started, and in some ways we have the template from what happened in NGA West, and we'll be working at that, but we've got our own task ahead of us. So the methods we're going to use are the methods as summarized by Yehua Zhang on Tuesday afternoon. There's a stochastic method by Pacific Engineering. There's a composite source model by Yehua. We're going to run XSIM. It's Gail Atkinson's model and with Dave Bohr. And then there are three of these kinematic models that are going to be used. One of them is the URS model, developed in large part by Rob Graves and Paul Somerville putting together this model. There's a kinematic model that uses scattering functions. The hybrid model, let me back up. The kinematic hybrid model of URS uses low frequency synthetics from a kinematic model, and then it adds to it the high frequencies in using a stochastic, basically similar method that is used in the XSIM model, but basically a Brun-type spectrum is added in, scaled with a particular stress drop, and then you have to merge high frequency and low frequency. There's a kinematic model that uses scattering functions. This is the one by San Diego State University, Kim Olson there, and ETH, Martin Mai. And this one again, in these three bottom kinematic models, they basically use the same approach for calculating the low frequencies. It's how do they calculate the high frequencies? It was an issue raised earlier by someone in the audience. And in the kinematic model using these scattering functions, SDSU and ETH, they use a 1D layered model. What they do is that they calculate the isochrone off of the low frequency part and convolve that with a scattering function. They've been using a scattering function derived by Yehua Zhang. Yehua has revised that now to a forward scattering function. Looks really nice, actually. And so they convolve that, and then they produce a high frequency part, which they then still have to merge with their low frequency. So it's how they do this merging of high frequency and low frequency that sometimes is problematic. The kinematic model at UCSB, which I partially described earlier today, uses the same sort of low frequency calculation. 1D model, if a 1D is what you have, it can do 3D as the other two kinematic models can do. And the difference is that the high frequencies are computed directly from that slip rate function, which has all frequencies in it, and the high frequencies are handled. The randomization is handled basically by randomizing some of the parameters on the fault, so that there's randomization of strike, dip, and the azimuth at which it comes into a station, and that then leads to the high frequency component. So they're different models. They cover a lot of areas. The RFP that went out requested that basically at that time it just simply said that there would be 7 earthquakes that would be simulated. Okay, and when they put it out, it was decided on in a conference call that these would be the simulation earthquakes. Okay, so you have the Imperial Valley strike-slip earthquake. Now, those who have worked on Imperial Valley know that, and I'll show you some of the models, what they look like. But, you know, we're supposed to be calculating for rock sites. You know, I was talking with Walt this morning, or this afternoon rather. I think there's one site that might be considered rock for Imperial Valley. All the rest we know are on soil. And then this very famous Saguenay earthquake, which is it an outlier or not? But it's, I'll tell you this, it's an interesting earthquake with some interesting data. It's a very interesting earthquake if you think at it physically. You're buried at something like 25 kilometers. You have a thrust earthquake. I mean, you think about the stresses if you're going to raise any part of the, 25 kilometers of ground, rock above you. So there'd be some high stresses. Loma Prieta is an interesting earthquake because it's oblique. It has a combination of both thrust and strike slip, and it's got a good data set. Not what we'd call East Coast hard rock, but it has, quote, California rock, and it's a big earthquake. So it's a bilateral rupture. It's interesting. Northridge, of course, is a classic reverse fault, buried, doesn't come to the surface, has some very high stress drops, obvious directivity. So it's got characteristics we'd like to have in our simulated earthquakes. Chi-Chi is the monster in here. It's a magnitude 7.6, 85 kilometers in length. The actual rupture at the northern end changes direction when you look at the best fitting models. It'll be a challenge. Totori is an earthquake that is a beautifully recorded earthquake, as I'll show you, in Japan, strike slip, buried. Very interesting earthquake in the sense that has a lot of slip that is shallow, and very interesting earthquake. Well recorded basically on the KickNet and KNet. So we have downhole recordings as well as surface recordings. And then we have this small earthquake, the Rivière du Loup earthquake, a reverse faulting earthquake, buried maybe at about 12 to 15 kilometers, and got some good recordings. So you look at Imperial Valley, it's strike slip. Most of the slip occurs at depth. This happens to, we haven't chosen which slip model we're going to use, and I'll come back to this. This model happens to be mine, so I favor it. But there's another really good model by Hartzel and Heaton, which is all sub-shear. But they have the similar characteristics, namely that what happens is that we have a fault where a lot of the slip is buried. It does break the free surface, but it really only had maybe 20 centimeters of slip at the surface. And it's a nice classic strike slip earthquake. You look at the Imperial Valley station distribution. So the names, should have figured out a way to make the names smaller, but these little blurbs. But you can see that most of these blue little droplets are all sitting in the Imperial Valley, which means we've got 5 kilometers of sediments, no rock in sight. There's one over in here at Superstition Mountain, Parachute Test Site. We might be able to get some rock. But we will do the simulation, and for scale, this is 50 kilometers. So this earthquake started south of the border. There's probably some bilateral. Most of it went to the north, and in my model, it triggered slip on the Brawley Fault as well. Totori is an earthquake. This comes from the model of Segaguchi. We will probably not use this segmented model, but one of the things here is that this is depth to top is only 2 kilometers up in here. There's a lot of slip that's shallow. This is true of almost every model for which there's an inversion done for this earthquake, and it's a good, magnitude 6.8 strike slip earthquake. And when you look at its station distribution, this is within 100 kilometers or so, and we've got lots. So the scale bar down in here, this is 120 kilometers. So if you go out 200 kilometers, we've got lots of stations to choose from. Our problem will not be in the simulations of choosing stations. It will be taking out stations we don't want to be looking at because we can't possibly afford to do this many calculations. And also we don't have the velocity structure that will go out all the way across here. But we'll have lots of choices. There's no question that we will have lots of choices for both rock sites, borehole sites, as well as surface sites. So no problem with that. Saguenay is this one that is really an interesting earthquake. Okay, this is a slip model from Hartzell. So we have a slip model we can start with. You can see that basically the hypocenter is down there at about 25 kilometers. It's a thrust fault. And now when we talk about the difference in recordings, right? So this is Saguenay, okay, same sort of scale. Yeah. It's a little bit bigger. This is 200 kilometers down here at the bottom, okay? So, you know, we're going out basically 200 kilometers to start reaching out to get some of these stations. But again, one of the things that we know about, you know, with Saguenay and other stations, I'll show one for the Rivière du Loup, which is even equally as actually more impressive in some ways, is the distance range at which you will get stations that are recording an earthquake. This is 5.8, so it's good size and it has a large stress drop, not surprising. But we will have a fewer number of stations when we get within 100 kilometers, and clearly we have almost no stations that are basically sitting inside of about 50. Chi-Chi is this massive earthquake, 85 kilometers in length. This is a model, a slip model from Zhang. We probably would use one by Kuofeng Ma or Chen Ji. They're better models for what this earthquake looked like, at least as starting models. But to get an idea of the problem again when we're looking at this is, I mean, the whole island, they had a wonderful network out there, and it will be a matter, we'll probably go back and look at NGA West, because they have a beautiful, flat file for this particular earthquake, so we know what the site conditions are, and we will have to select which sites we're going to do validations against. It might be interesting actually to do validations and then leave out some that weren't used and make some prediction about sites that were never looked at. So, Loma Prieta, of course, we all know about because it happened up here in 1989, the World Series earthquake, and got different. It starts off fairly deep, but some of the slip is deep, some of it's shallow, and it's a pretty complicated event. But it also has a large number of stations basically oriented along the faults where most of the stations are, and we can go out to pretty good distance. But again, there aren't a lot of rock stations in this. These in Halls Valley may be one, Calaveras Reservoir, but some of these stations are not going to work out so well, but we've got lots of stations in good distance. This is the one that is the smallest of the group, this one in northern, basically on the St. Lawrence Seaway. I took this fault plane solution from Bob Herman's website, and it's a thrust fault. So we know it's a thrust fault. It's buried at about 13 kilometers, and this is the scale out here is 1,500 kilometers down here at the bottom. This is about 1,500 kilometers, and these are stations that triggered by this event. So, I mean, we have this little earthquake up here, and down here, several thousand kilometers away, you can pick up, that you could get a recording station if you wanted to do it. So it's a really good one if you're going to be, I'm not sure that these are horizontals, they're probably verticals, but you can certainly get a lot of stations. More likely because we're going to be looking in close. The scale is now changed by a factor of 10. Yeah, it went from 1,500 for a scale down here now to a scale of 100. And so, but we have a lot of stations in close. In other words, there are several stations in here. I'm not sure which ones are vertical or not. And then Northridge, similar sort of thing with lots of stations that we can play with. Well, the issues with all this in this finite fault simulation is that in all of these, we will have to agree as to what will be the velocity structure that we're going to use. Okay, this is, we're going to need not just VEF, VP, and density. But one of the most important things will be understanding, well, what Q models are we going to use? Because there's a strong trade-off, as we've heard earlier in these 4 days, between Q and 1 over R type attenuations and the like. And so we have to know what Q we're all going to use and how we're going to incorporate them, or what is let's say, the effective Q in some cases for models, let's say the stochastic models. What is the effective Q if you, in fact, you also have layered models in which you're inputting Q into individual layers? So this is going to be an issue. The other one, I'm not sure exactly how the San Diego State ETH model will work, because in fact they have to use a scattering function. It's an elegant idea, and if you could get the small earthquakes, you can get the scattering functions for the region. And it's a matter of, exactly how these models will be tuned, okay? But there is an issue basically of making sure that we have, in some ways when we're fixing the parameters, because as we go to do predictions for earthquakes we know nothing about, we need to know again which of these parameters are going to be fixed. And part of fixing it is not fixing always the source parameters, but we have to find a way that we systematically know how do we choose, or what is the basis for choosing this velocity and attenuation structure in which we embed the earthquake. Now, one of the difficulties which we have not addressed and we will have to have a meeting of this validation group, is we have to, everybody put into the RFP exactly what parameters they were going to hold fixed and which ones they allow to vary in their simulations. But the whole group needs to actually have this Excel spreadsheet in which all these parameters are in fact decided upon. I think it will be, it's accounting basically, but we have to do it, okay? But by itself, this is not going to actually test the validity of these methods for making a prediction of ground motion in the future, okay? And in some ways in the validation procedure, we have to say what constitutes ground motion prediction. And what are the metrics for describing ground motion prediction? Well, the standard ground motion prediction metrics have been looking at response spectral values, looking at the standard deviation and the bias. And if you think about that, as you all know here, I'm just preaching to the choir, this is a frequency method. Okay, time is taken out. You figure out a way. Basically, you take you calculate the response spectrum from the time series, but you're looking in the frequency domain. So you're not seeing how things come in time. I think that it's very useful to look at any of these methods to see how well they predict, regardless of what they're doing, but just exactly what is the trend that they have for PGA and PGV. Remember that all these methods are supposed to calculate, out to some distance and out to a very broad frequency band, 0 to 100 hertz. Now, they may not go to 100 hertz. If Q wipes them out, we're certainly not going to calculate zeros. But the thing about it is that just seeing what the trend is of PGA and PGV with distance, it's worthwhile. I don't know exactly how you, unless you want to fit a curve through there and then compare your data, it's very hard to say, well, exactly what are you going to use as the metric. You could do least squares if you have a well-defined curve. You could just simply plot your points against it. But if you're just plotting it against data, it's possible to do sort of like a KS test and treat them as just two different functions. I think that we could do least squares fit to CAV. It's time domain, and it would include duration, but how is duration defined? And CAD, and I'm going to show it on the next slide. This is a made-up one. Areas intensity is another time domain issue. Hausner intensity is a response spectrum. There are different metrics, and each of these metrics basically are a function of distance. So we are looking at things which are in fact a function of distance, which of course I think people want, but we have to find out, we have to define these metrics, and we have to define them before we start doing the simulations. I think you shouldn't be defining your metrics after the fact. You should know basically, okay, what you're going to calculate it, and then just see what you get. Now, this CAV is a well-defined quantity. It's the integral of the absolute value of acceleration over time, 0 to TD, some duration. By analogy, you could have something like cumulative absolute displacement because you'd be sampling a different frequency band, giving different weight, if you were to then look at integrate the absolute value of velocity. This is a parameter that is being computed, and it has time in it, duration. It's tricky because I haven't said, well, how do you define duration? I don't know. I mean, I can give you my estimate, but, is there some way to define it that makes it useful all the way around? And of course, Hausner intensity has been around for quite a while. So there are methods of looking at these parameters that are well defined. And the reason I want to put in a pitch for something like cumulative absolute velocity or cumulative absolute displacement is that if you think what those curves look like, those are monotonically increasing curves, okay? Which means it's very easy to do that with the data, and then it's very easy to do a least squares fit between them. It looks like, it's like a KS test. In other words, you compare distributions, you just compare the difference in two monotonically increasing functions. You can find different measures. You can find deviations or you can find least squares, but it also involves time because it's like the very short pulses that we saw Martin showed the other day with, they don't look like the data, but they might produce PGA and PGV very well. But do they provide a duration estimate in the same time? And so you want things that basically, you want a robust estimate of what your ground motion prediction is. And it's hard to know what those parameters should be. So some of the issues that I see our group having to work through is just how do we find a velocity and attenuation structure for each event that is consistent between all methods? It may not be possible. But we have to have some way of knowing what that is. In other words, we have to know how much of a difference is attributed. Somebody has to use one Q value, okay? Some people don't use Q of F, some people do, but the question becomes how are we going to find, structures that are consistent? But we need it for all 7 events. There's a real good question, which slip model will we use as our initial model? Okay? In many ways, if you think about it, and Paul and I have talked about this, we use a slip model, let's say Northridge. So we use a very good model by Dave Wald and others. And you get a good model, and by definition, if you put that model into your low frequencies and you use their velocity structure, you should, in fact, fit the data in the low frequencies just as well as the inversion that got to the model, right? So you're not really testing too much about the low frequency or the slip distribution. What you're really testing is the high frequency part. And in some of these cases, more than one model exists. For Loma Prieta, I can name 4, models. For Northridge, I can think of at least 3 models. I know that for Totori, there are at least 3 or 4 models that exist. So there are different models, and do we want to be confined to one, or do we want to see what the range of the output motion is instead of trying to make such perfect fits? What we're really trying to say is when we look at all these different models, does the data, let's say a PGA or response spectral ordinate, lie within the predicted distribution of ground motion that these models predict? Okay? I think that we will have a problem of, this issue about how do we test, the validity of the methods when we already know the model. Okay, that's one thing. But how well does that tell us how well we can predict the future earthquake ground motion when we don't know what that slip distribution looks like? It's not easy. It's something that we're going to have to work through, but I think that it's a good group. We're going to have to look at the metrics. In other words, there's got to be more than one metric. In other words, it may be that true for this particular, the goals of this particular exercise overall is in fact to determine response spectral ordinates for eastern and central North American earthquakes. It's true, but the issue becomes how do you know that you're doing this if that's all that you target? In other words, so I think it's out there that these, we're going to have to come up to grips with this. And I think one of the biggest issues for us will be, as you can see from some of these earthquakes, we don't have unlimited time and unlimited CPU power basically to keep going and running all different stations, et cetera, without, it's not so hard actually to have a computer do it, but it takes a lot of time to sit back and analyze it. In other words, that's where the time is taken. When you actually sit down, you look at the comparisons, what you're doing, it's one thing to run models. I mean, we can run lots of them. There's no problem. But it's really when you sit back and analyze the data, and you analyze your synthetics compared to the data, it takes time. And so doing 100 different stations at Chi-Chi and 100 different stations for Totori, we're talking about a lot of effort that goes into it, and that's just a little bit beyond the scope of where we can be. But unlike the two predecessors here today, I do not have a layout of exactly what our plan is because we haven't actually met to sit down now that we know which stations which earthquakes we're going to be looking at to say exactly what the steps are and then, the next steps will be. But our plan, I will be calling a meeting of these individuals, and we will have to work this out in a hurry about exactly choosing the stations, choosing the velocity structure, and then getting on with the business at hand. So we'll get there, but I think we're going to be a little bit slower than what Norm or USEF would have preferred. So that's all I have to say for today. Now I will duck. I see Norm over here saying, writing like crazy.
So the final validation plan is not ready yet, but you guys met and selected earthquakes, and I mean it's in process. I saw the PPRP getting scared. No, it's in the process, right?
It's in process.
Okay.
We have a process. We know which earthquakes we're going to deal with. We have a good idea of their geometry. We have a pretty good idea of slip functions. I think we certainly know what the velocity structures were that were used to invert for those particular slip functions, so it's certainly worthwhile. I think we have to be sure that what happens is between those type of velocity structures, the different methods use different approximations to it. And so, for example, if you use a stochastic source model, you basically have a 1 over r, you have one shear wave velocity, you have one p wave velocity, you have a q. Okay? How does that compare when you're in fact comparing that to somebody who's got 7 layers, a plane layered structure? How do you make sure that you define, the arrival times, et cetera, such that you have an effective, let's say, an effective shear wave velocity that is consistent for those 7 layers that the people who are running the layered models are going to use, and the same q, so that you know that you are in fact somehow in the same ballpark. Otherwise, you're just comparing, apples and pomegranates. They look red, but they're not exactly the same fruit.
Yeah, so I think a considerable effort will be put into that, like we discussed yesterday, that you might have physical parameters or conceptual parameters that make sense, but the way they're implemented is really model dependent, and there might be different variables or inputs that come and affect those. So I think this is a challenge in itself, but it will need to be done. And I think one of the major issue that we always have in the back of our mind, that's why you want to look at more than just essay and duration, is that we're doing the validation to make sure that the codes work, but we need to think in a forward sense. So if the duration is not consistent with the magnitude in a forward sense, that's why we want to capture that when we validate. So I think that's why Ralph was bringing all those issues. It's really important because they're going to be used in a forward sense, and we need to be able to capture this. Any comments or questions regarding the finite fault validation draft plan? Yes, Walter, please come over.
So how did you choose those particular earthquakes? Because there's a couple that I would have included that, is that list closed or is it, open for expansion?
The number is fixed at 7. And we chose those because of the distribution of, we needed a range in magnitude and a range in mechanism, but we also needed a range, geography. In other words, we have to have some that, we do not have any wonderful, let's say 6.8 earthquakes in the east that are well recorded that we can use. So we have to deal with what we have. And there are big issues about whether or not you should use Saguenay or there's another one, Val de Bois. But in essence, we're trying to see not whether or not we can say, well, can we predict exactly this? But what we want to do is predict the range of ground motion that we would expect from different sized earthquakes and different mechanisms that are representative of what we see in the east. Looking at Bob Herman's website and checking all the focal mechanisms last night, in fact, going through most of them, you find out that basically in the northeast you find thrust earthquakes. In the Midwest you generally find strike slip. Don't see a lot of normal. There are some. But for the most part, what you see are thrust earthquakes and strike slip. And so these earthquakes represent that type of earthquake. But then we wanted something big. And the only well-recorded, really large, well, not the only one. Wenchuan is a very large thrust earthquake, very complicated, multiple strands, but a long way from actually being analyzed to the point where we understand well enough about what happened. But Chi-Chi is well recorded, used in the previous analysis. So, yeah, we could have chosen other earthquakes, but we had a list. Norm had about 10 or 11, and then we winnowed it down to 7 because that was in the RFP. Yeah, we did consider Mount Carmel. There's another one.
Well, there's 2 parts to the validation. We are running a validation on the point source models, and we're running them on the finite source models. The point source models are easy to implement in a very efficient way, and so those will do many more earthquakes. So essentially all of the eastern U.S. events, relevant ones, will be included. I think we were looking at we looked at the distance range that was covered by the different events in the east and their magnitude. So we were trying to get a little bigger magnitudes for the finite source that we could, yet mainly finding things where we had data, let's say, from 10 to 100 kilometers that we could actually pick up. If it was all at 50 to 100, then it's not really going to help us really constraining part of the geometrical spreading out of the, in this case, Green's functions out of the validation. So we did look at all those. I think we considered everything that, we considered all the earthquakes that were in the flat file, the Eastern U.S. flat file, if you've seen that list that Chris Kramer's set. For the folks doing the validation, some of them are more efficient than others, and so we give them a minimum of these 7 to do, but they can do extra to the extent that they want to crank them all out. But we wanted to have a minimum that we could compare the different models on.
Okay. So is that it regarding the validation? So it's not just finite fault, as in your titles. It's simulation validation, and it's a simulation working group. But, yeah. So, anything else? You want to move along with your summary of the day? And then I'll do a summary of the week in a much shorter time. Norman's going to do it first. For the record, Ralph recently accepted the chair position within the simulation working group, which was before held by Norm. So there was this handoff right at the time that we selected those earthquakes, and Ralph obviously was involved because he was in the group. But I mean, there was a transition in there that recently happened.
Day 4, version 2, I think. Okay, so I'm going to quickly go through the things that we talked about this morning. I think that the part this morning had a little more clear issue of what our data needs are going to be. Just as a reminder, the whole issue of dynamic fault modeling is to get at our kinematic model inputs. The models that we looked at, some of them, for example, we need to make sure that models, if they have correlations, they can cover all the cases that we have. The model that Ralph showed that Jan and he had worked on was for strike slip sub-shear, so we don't have strike slip super shear or reverse from that particular model, and they really found that the correlations were different from those. What this is going to come back to finding out is in the 100 runs project, did normal faulting, but they haven't looked at the correlations. They're just getting those values coming out of it. A key issue that came up was, as Paul Spuducin said, well, how do we check this versus data? And I think the one approach that we got here, possible thing for us to look at it, is actually trying to implement these models, the rupture generators, to generate suites of models for either cases that are in ground motion models or actual past earthquakes, and then see how those work in sort of forward prediction of the models to see how they predict past events. I think in the end, we're going to have to look at a bit at this part. If we're worried about correlations, do they really matter that much in terms of the whole impact on the ground motions? Because again, we could have a very interesting, important correlation that shows up that is not relevant to the ground motions we're after, but we want to be sure if there is an important one that is relevant that we capture it. Super shear versus sub-shear ruptures. So there was talk again about if the correlation structure is different, we need to basically address how many, what's the fraction of ruptures that will be super shear versus sub-shear. There's a comment from Paul Somerville whether or not this is a critical issue from the eastern U.S. I think that might be the first thing that we just set up a task to just consider, is this a problem? I know that we've talked about pieces of rupture being super shear or not. So that would be a way to see how much effort we really need to put onto that topic. I'm going to mainly focus back on the bottom here. That is what Rob went through in summarizing the available models. So there's quite a lot out there for kinematic rupture model generators to pick from. And he noted that a couple of those were on the SSHAC broadband platform, which made them easy to use. But that's not our classification of good versus bad right now, or models that we need to consider. What wasn't talked about this morning, and that I think we have to get back and fill in, is the stochastic finite fault method generators or approaches, and if those can simply use the, let's say, simplified versions of the more complex rupture generators that give you more information than you may need. Can you just pull out, if all you need is rupture velocity, then maybe you can pull that out of there, or do you need a couple of parameters? So one of the topics along this line here is, yesterday we again talked about the, let's say, stress drop is not, point source stress drop is not a fundamental physical parameter that we're measuring. It fits with the rest of the model that we get. How much can we take these rupture generators as generating actually physical parameters that then we would simplify into a stochastic model, versus are they generating parameters, again, that fit with a particular model? And this gets back to this whole issue. It sounded like in our discussion that Rob said the intent was that they would work for all methods, but I think that's still something we need to discuss with the modelers, or those people who have developed the methods we're generating, or the 6 ones we're going to apply. Is that really the case? Should these things be independent, or is there something more correlated? And I could see here, I was thinking through this, it may be, even if you generated suites of kinematic ruptures from a method, that a particular, say, stochastic method may find that it doesn't need to use the rupture velocity that comes out of those, but maybe it's 1.5, 5% higher or something like that to get it to work. It could be that it needs some other adjustment off of those factors as what is the proper input to the model. I'm just not sure about that, but I think this is a topic we're going to have to address in our simulation approach. I'm going to come back to that one. So then on, back already. Variability, so our kinematic parameters are trying to get us to get a stable estimate of the mean parameters of the rupture from our generators, but we'll also be looking at them for their implications on sigma and how they would get to basically this parametric versus modeling variability terms that we've used in the past. So let me then jump to what sigma is. This is kind of hard to see, sorry, it's small. The key is right now we don't have enough data. The flat file that exists doesn't have enough data with repeated stations to look at sigma in the east, or single station sigma in the east. So we do have to add data. I think the data sets we are talking about for Bob Herman will address this. But as we talked on the first, was it the first day? It's all a bit of a blur now. There may be additional small magnitude earthquakes that we can pick out from particular areas which we would select because they were recorded at, or would add recordings at stations that had a few but maybe not enough recordings yet in the magnitude 4 and larger range. I think our goal is to keep this above about magnitude 3 in adding in any events that we're working with here. There was a comment, question about, well, how do we use these data and how do we get residuals? So there is a task that is deriving a new ground motion model consistent with the small magnitude data in the east. That is not the model that we are producing in this project, and it is only intended to get mean-centered residuals out that can be used for looking at sigmas. So what we've talked about, that this is not sigma and is pretty stable compared to the complexity of the model, so we think we can do this with a fairly simple model. We want to make sure nobody thinks that this is our initial version of what the answer might be, because these will not extrapolate properly to high magnitudes and short distances. And then really, I think the task that Linda laid out on how we're going to get to an empirical single-station sigma has a whole lot of steps that are fairly straightforward in getting there. We know we've seen this happening already for the Pegasus project, so we're pretty confident this will work. But we need to look at the simulation results, and that is something that we haven't really laid out. This past approach that we've used on other projects of the modeling and parametric separation term approaches probably as a starting point. And we need to, though, I think, really think about this whole assumption here, and that is that our validation earthquakes and the misfit we have with those captures all of the sins of our model and where we want to apply it, right? So whatever effects that are not in our model but they're in our validation data, we will be moving to the east, to our sites in the east where we're going to apply them. And I think this is worth thinking about this one more time. Additional data sets that could really help us out. So the Western Australia data sounded quite promising, even the additional sites. If I got this right, what Trevor said, maybe 60 earthquakes in that sequence. That's and that have been recorded at more. That there'll be sites that have recorded easily more than 10 earthquakes. We would have another really good set to start to look at. And then the Wenchuan data, there is another large number of aftershocks that can be brought along. So this is a topic, again, as I mentioned, around the world that is really getting a lot of attention, and I think we're going to benefit from all the other aspects or work that's going on this topic right now. I did the clicking thing. There's a talk about aftershocks, and we're really going to have to pay attention to this. I am now much more aware of this. I hadn't thought about this before, but I think this is a really important comment that if we've got an active aftershock sequence, we could really be fooling ourselves into a very low single station sigma, which is becoming, the default single pass sigma. And those numbers are really different, and we want to not be caught off guard there. The note we had here, the Chon-Young's model actually found it went the other way. But they weren't looking at really active aftershock sequences in doing that. The plan for empirical data, I think, again, is clear, and the whole issue of what are we going to do with the numerical simulations is going to be an issue. Here, from the small magnitude, our plan, again, comparing the small magnitude data from California or other regions with the magnitude data and magnitudes and distances that are similar in the east, and if they're similar, at this point, one assumption then is the higher magnitude sigma would also be transferable. And that will be part of our interpretation of what to do here. If they're different, it's not clear what to do, and Saguenay is going to be the big issue. So that's not something we resolve today, other than we know Saguenay is there. I'm not sure there's anything else we can be doing on Saguenay. One topic that didn't come up in our sigma issue here, I think we had mentioned when we met with the TI team a bit yesterday, is back to looking at teleseismic data and how does Saguenay fall so that we can get a larger number of events, looking at how Saguenay fits into that evaluation in terms of we've looked at before MB and MSs or whatever it's going to be, but there may be some way to try to judge Saguenay's, is it typical or is it anomalous through, I'm going to write that down so I don't forget here. You can fix that later. Okay. You don't hire me for my spelling. Okay. That's all I had I think captured our discussion on sigma. The rest of the plan I think is fairly straightforward. V over H, what Nas showed is we have a bunch of recent models for V over H, but nothing really for Eastern United States conditions. So that's the big part of it here. Our agreement, or what we understand now, is we will include some epistemic uncertainty in the V over H ratio that we're bringing along, but it will be a much simpler form of a logic tree than all the more complicated or complete treatment that we'll be doing for the horizontal by itself. For soil sites, this is going to be a consensus model, not subject to center, body, and range in a similar way that we're doing the site amplification factors for the horizontal. And so I was talking about the plan of looking at the analytical models for the V over H ratio with near vertical P waves and inclined PSV or SV waves. That's all straightforward, but we really at this point have a need to figure out what are we going to do with those two sets of information. And it's not clear to me, do we just take the P wave number above 10 hertz and the SV one below 10 hertz, or is there I don't know. So I'll just leave that this is a problem we're going to have to develop an approach to figure out how to deal with this. The geotechnical industry, as I said, really haven't solved this problem or dealt with it very well, so they're not going to be much help, I think, from past practice, but this will be an issue to get. We talked about, there's mention of additional data that may be relevant from the New Zealand earthquake, and Youssef mentioned this is already in our NGA database that's being brought along right now. And that's all that I have for today's data needs and issues. Okay?
So that's the time where we come in and offer the audience to comment. First, the PPRP. Do you have any specific comments pertaining to today's topics and regarding norm summary for today, or it's going to be done closed doors? Or I'm going to do a super quick week review after this. You'll see that slide through. Yes, please. Yeah, please come over. Leon Wright. Leon.
Yeah, Leon Wright. I have a question for Linda. Linda, in your list of tasks, one of the things you included was truncation. And I don't think you spent too much time on it. This has been a topic, a lot of blood, sweat, and tears has been spent on this. I wonder if you tell us what you aim to achieve, how are you going to achieve it, and what's the likelihood of success?
So the reason why I didn't spend a lot of time on it is because it's just added recently, so we haven't actually discussed it in our meetings. But I think that it should be straightforward. It's basically Norm has a paper where he tests the application of the lognormal distribution based on the data, based on the probability of the events in the data set, the recordings in the data set. Right?
Let me see if I can help you a little bit here. So what Linda is saying is this task was added based on the discussion, I think either Monday or Tuesday, saying, are we going to look at that? So we said, yes, we'll add it to the Sigma working group, part. So I wouldn't say it's straightforward. This is something we've been working on for quite a while. I think what we're going to basically do, probably start with a lot of the work that's been done on the extreme ground motion project for Yucca Mountain, which has looked at that distribution in almost every possible way. So, and other recent evaluations. But I think the likelihood for success is very small, other than physical limits as opposed to anything where we're really truncating the distribution on any statistical basis. So.
Thank you. Yes, comments? After I do the quick week review, I'll remind you of what we went through this week, and some things might bubble up, so we'll do another short round of comments. For today's comments, go ahead.
Just thoughts on this topic. There was some very positive, interesting discussion, useful input from Gabe and others on the V over H. Clearly, if you've got the sensor body and range on the horizontal motion, that convolved with whatever epistemic uncertainty you put on the V over H ratio shouldn't end up with more than you would have got if you did the vertical separately. And I think you kind of agree that you don't want to blow up the epistemic uncertainty on the V over H and consequently on the V. So the only thought is how much, therefore, the V over H work needs to be inside a SHAC level 3 process. The thought, as we discussed yesterday, the same thought about some of the site amplification issues. One of the things you were discussing in this was site amplification for the vertical motion, and I didn't hear any reference to whether your geotechnical working group could help you on that one. I don't know. You have a group assigned to site response, and that's a site response issue.
We have a group assigned to vertical site response in the NGA West, and they're taking the lead on that part. So the V over H is a mixture of the two projects. That's really what's going on. Do you want to answer that?
Yusuf Hashash. We discussed the issue of vertical site response extensively in the working group. But since we became aware of the effort on NGA West, we thought that it would be prudent to first let the NGA West start with this effort, since there's more data, better basis for the development of models, relationships, and then from there we would take it over and see if we can apply it in NGA East. So we didn't have it in a formalized way, but that's how we agreed within the geotechnical working group on dealing with it, and I'm now maybe stating it for the rest of the project. That's our plan.
Any other comments from the PPRP? No? Yes? No? Okay. We open that up to the sponsors. JMC, you have specific comments for today? Okay, let's open that to the observers, everyone. Anybody has comments on today's topic? Quick. James Bella.
I'm James Bela, President and founder of Oregon Earthquake Awareness. I've been left wondering what a New Zealander would say when he was preaching to the choir in Christchurch, but I'm actually troubled by the 7 earthquakes. It just seems to me that if we're going to model earthquakes and we're trying to come up with design parameters for the central and eastern U.S. and Canada, I guess I would feel bitter about the effort if we actually modeled earthquakes that were occurring in this region rather than Chi-Chi and Imperial Valley and so forth. So that's my comment. I also have some comments on the weeks, but maybe they're appropriate after your summary, or?
Any other comments on today's specific topics? Okay, so let's move on to my super quick overview of the week, just to remind ourselves what we went through and what we talked about. And for that, Carola here is going to help out. By the way, I would like, before we finish with all the thank yous and all that, to acknowledge all the help of the postdocs who are overly skilled people to help us with tasks that are fairly simple, including the registration with Tim and Cheta, Carola D'Alessandro, and Camilla Burton, who helped with loading all those things this week. We had such a great group of skilled people to help us out with things. And also, I would like to thank the peer employees, including Heidi and Yolanda, who really made this possible, even though we had a difficult room to work with. So I'd like to thank them. Okay, so what is our objective? Within the SHAC process, again, this is a SHAC Level 3 process, and we went over that in length earlier in the week. But if we look at this, then our objective is really to provide the best estimate of the distribution of ground motions. That includes PGA, PGV, SA at 5% damping for a wide range of spectral periods on sites located up to 1,000 kilometers from future earthquakes in SENA, with magnitudes in the range of 4 to 8. And to provide for rock sites, this is for rock sites, and to provide the epistemic uncertainty associated with this estimate. So we really want to cover the center, body, and range. So we include the variability of the parameters and the epistemic uncertainty in that logic tree. So that's really our goal, okay? And also, in trying to reach that goal, we have to go through a lot of technical discussions. And what we want to capture from that, given that there's not a lot of data in these, we know we have to rely on simulations. And we want to capture, in the end, what really matters for the PSHA results, and that's going to be the simulations and the input to those simulations. And as we have discussed in the last couple of days, a lot of correlations inside with those parameters, be it with Q and or geometrical spreading, or if we go deeper in the slip rate and rupture velocities, if we go really in the nuts and bolts in the models, and all those correlations are model dependent. So that's really a place where we need to spend time, because it's going to impact our hazard. So again, we might sometimes steer away from things that look interesting, but it's only because what we care is, does it matter for the ground motions in the end? If we had unlimited time and budget, we could finish this project in 30 years and be happy with all the details, but that's not what we're after. We also want to capture then the center, body, and range of all those inputs, and by doing that, we hope that it's going to make a more stable product over time. The SHAC process also allows for this transparency, and the fact that we're government funded makes us share with everybody in the public. By the way, we'll put all the presentations from this week on the website. It might take after Thanksgiving. Just give us some time to regroup. But that's really what we're after here. So we need to be transparent about the process, and we also want to document everything very thoroughly so that as we gather new information, we know where we can change things or how it's going to impact the hazard ultimately. Okay. So the technical plan. I thought I would go over the tasks that I presented on Monday, kind of summarizes what we're doing, and briefly remind ourselves what we went through. One of the tasks that's very important is a compilation of available ground motion data in SENA and other relevant data in other stable continental regions. And although the prelim database was presented on Monday, throughout the week we have identified the areas where we need to gather more data to resolve one issue or another. Now we'll need to compile all that, strategize, and decide where we have the most bang for our buck, given, again, the feasibility to see what we can really do with that. So database is still an ongoing effort, and we have already identified a few sources of additional data, but we need to go through that. We also needed to identify and evaluate currently available simulation methods, and point source, finite fault, and all that. We need to assess the required input parameters, and we're still going to have a lot of work to do, as Ralph alluded, and even what Rob presented, that, again, everything is model dependent. Then once we have done our validation in the next few months, we will select a subset of simulation methods to develop the database of ground motions that will then be used by the ground motion prediction equation developer. So then we come to that part, which we didn't talk about much this time because it's premature at this point, but we will have an RFP to invite GMP developers to develop suites of models for each data set. It could be just point source model, single corner, double corner, if we have finite fault, and we'll have different sets of GMPs for each of those. And those GMPs will represent the median ground motions, because sigma, as you saw today, is treated outside of that. We will develop a method for addressing vertical motions and for site response. Now, these two items here are not part of the final SHAC process logic rebuilding. It doesn't mean these topics are not important, and we have also other sponsors who really want this. And in the end, if you want the products from this project to be used, we will need to provide other tools than just ground motions on hard rock at 2,800 meters per second. So these projects might not fit in the overall SHAC Level 3 review process, but are still critical to this project in terms of having a final product that's consistent. We will have a suite of alternate models for the single station sigma that we covered today. And then after many iterations and discussions and work, we hope to get that logic rebuilt and have it evaluated and move on. Again, throughout this project, we really want to document things thoroughly. So the next step, if we just look in the very immediate future, the TI team will regroup and will need to condense the summaries from this week and everything that we've gathered in terms of new tasks, because there were many new tasks identified to solve some of the critical issues that were highlighted this week. We'll also need to prioritize the data gathering, as I mentioned. So we need to assess the feasibility internally and with the working groups that are involved in each of those tasks, And we need to prioritize in terms of budget, and what we can do and how we can get the most bang for our buck in terms of what matters. And then we'll need to identify who's going to do the work. And so once we have integrated these things in the draft working plan we have, then we'll have a better working plan. We hope to have a good project plan that's clearer for everyone to review, and we'll circulate that. That's going to become our Bible, what we follow through this project as we move forward. So again, then the next step after that is just going to be to do all the work and to document it, and that's going to be a task for everybody who's involved in the project will need to contribute to a certain level. I want to remind you that the SHAC Workshop 2, the date has been changed, but now it's stable. We centered it around the room so that we have a better room to do this workshop, and it's going to be in Davis Hall. So it's May 31st to June 3rd, and you'll be reminded of that, and you'll receive emails from me regarding that. So before I pass to Youssef, I guess, do you guys have any comments that relate to the week overall? I didn't review everything in detail, it's just too long, but Larry, please. Yes, please come over. So general comments on this week, and yes. So I guess we'll go with the PPRP first. No? Are you okay? We'll go anti-SHAC and reverse the role sponsor first, and then PPRP. Please, Larry.
I'm perfectly willing to yield to the PPRP from a lot of practice. Let me just emphasize on behalf of the sponsors the appreciation that what everybody has done this week. It's a complex problem with a lot of inputs, and I think we're well on our way to achieve the goals we've seen this week. So I did want to go on the record to thank everybody. I also want to further support on behalf of the sponsors Norm's point and Christine's point about getting to those issues that really affect the bottom line to achieve the product. With that in mind, each working group should think about their sensitivity analysis that would help them get a better feel for what's important. And so we should see in the project plan very transparent in the approach that would allow an understanding of those critical issues.
I've been told to identify myself. Julian Romer, Chairman of the PPRP. Very briefly, because we have every evening, and we're going to have now a debriefing with the TI team and the project manager. But we want to go on record to say the following, and I'll be just very honest. When we met as a PPRP on Sunday afternoon to discuss the draft project plan, I think I would be correct to qualify our feelings as grave concerns. We acknowledge that this is a project which began as a technical project as the NGA West, but with a much more ambitious task of transmitting that to the East, and it's had to move into the complex clothing of a SHAC Level 3 project. We've gone from being gravely concerned to, I would say, impressed and optimistic. I think it's really taking shape. The organization and the presentations and the discussion have been increasingly improving over the week. We've seen a very effective TI team. And just to embarrass you, Christine, I think this project has given birth to a very impressive new TI lead as well, in the person of your good self. Thank you.
Thank you. Thank you. And one thing I forgot to thank everybody actually to really helping in making this SHAC process work this week. It's the first time I tried to enforce those rules, and I know I was cracking the whip on all of you, but it was great. Everybody worked well within that framework, and thank you to all the presenters who spent that time in here. Is there any other general comments from the public on the week? If you can make that concise and NGA East focused, please.
James Vila. I wanted to summarize using some comments from people that couldn't be here. Mark Twain sent me this email. It ain't what we don't know that hurts us or gets us into trouble. It's what we know for certain that just ain't so. And Einstein said, not everything that can be counted counts, and not everything that counts can be counted. And importantly, changing your mind is the only sure sign that you have one. The only ones who always find what they're looking for are the fault finders. And what we think is order is only the current reigning form of chaos. Warren Buffett sent, beware of geeks bearing formulas. Henry Ford said, if I had asked people what they wanted, they would have said faster horses. Science is organized knowledge, and wisdom is organized life. In the earthquake...
Please keep it focused to NG East, please. As much as you can, okay?
Look how often the unexpected happens, and yet we still never expect it. Enrico Fermi, before I came here, I was confused on this subject. Now that I have heard your lecture, I am still confused, but on a higher level. To every complex problem, there is a simple answer, and it's wrong. Richard Feynman, geophysics is like sex. Sure, it has practical applications, but that's not why we do it. Basic problem in this approach for the week is the data is unreliable, but the conclusions are fascinating. On the way down here, I actually had the opportunity to eat an apple and an orange. And I did a peel review, and I can tell you that the similarities are different. And the similarities between the SHAC Level 3 process and the earthquake problem are very different. Some of you know that the SHAC Level 4 process was found to be unreliable in the Pegasus project. The problem with the SHAC process is it gives you...
It doesn't pertain to NG East. We want comments regarding this week. And do you have specific comments relating to the discussions we had this week?
I'd like to protest the interference of the chairman.
Please, we're keeping it to the point. That's all I'm asking you. We're welcoming your comments. Just try to keep them to the point of what we're trying to achieve this week. That's all I'm asking.
Well, you're trying to achieve something that's not achievable with the SHAC Level 3 process. And if we look at earthquakes in the last 10 years, the actual earthquake ground motions have exceeded the PSHA estimates by factors of 2 to 4. These include Kobe, Japan, Gujarat, India, Bermudes, Algeria, Bam, Iran, East Sichuan, China, Haiti, Landers, and Northridge. There's a copy of this in the back table. If you run out of copies, leave an email. You can get one. There was a copy in Nature Geoscience that showed that the Wenchuan earthquake violated every assumption in the PSHA methodology that the U.S. GEOS does in the seismic hazard. I think for nuclear power plants, it should not be limited to just SHAC Level 3 process. There needs to be a reality check, such as what the Japanese are doing with scenario-based I wouldn't object to the NGA East effort if it included all avenues of seismic hazard estimation. The history of seismic hazard mapping in California is also on the back table. And in that history, it details the politics behind how PSHA defeated DSHA.
Okay, I'm sorry, James. These comments are very long. We will welcome them in writing, and we'll read them. But I think at this point we need to move on and let other people have their comments as well. Okay? Thank you. Annie, on behalf of the sponsors, I think you had a few closing comments. Thank you.
Hi. Well, started out the week about 4 days ago, but really we started this project several years ago. And I think that, as Larry mentioned, on behalf of the sponsors, I think that we are extremely pleased with the way that the week went. I think we see that this project, as a complement to the very successful Level 3 CEUS SSC project, which is towards its end, is really going to change the state of practice in low to moderate seismicity regions, not only within Central and Eastern North America, but also globally. And I have to give credit to everyone who's been involved, the TI team in particular, and I concur that I think we have an outstanding TI team and are really on the road to success. All of the working groups whose tremendous efforts we've seen. Have to thank the PPRP for their very thoughtful and helpful comments throughout the week, and we'll hear some more of those in a few minutes. The input of the many resource experts, evaluators, and everybody else who's come to participate in this week. And we thank the participation of those who've joined us over the phone and who've been listening in. I think this is the first of several SHAC workshops, and it's been extremely useful and really achieved the goals of the workshop, which is to identify the data needs and the critical issues that we need to think about to really make a complete project moving forward. And so I look forward, along with the rest of the sponsors, to seeing the project progress, to hearing the proponent arguments, which will be occurring at the next series of workshops, and to watch as this project moves forward over the next few years to its successful conclusion. So thank you all very, very much for participating.
All right. I'm really pleasantly surprised that you all survived 4 days. I wanted to thank sponsors, NRC, DOE, EPRI, TIA, and also a great TI team and PPRP. I like to thank all the experts that they gave very thoughtful comments and on technical issues. And also I like to thank all the observers for attending the workshop. As we mentioned, we will have other non-SHAC technical meetings at the working group levels or higher level to communicate with the community. We will have it. But as Christine mentioned, our next formal SHAC workshop will be May 31st to June 3rd at Berkeley, just 5 minutes from here. So thank you very much, everyone, for attending the meeting, and officially the meeting is adjourned. Thanks a lot.